Hello, my name is Alan Roebuck. I'm the past president of the Atmospheric Sciences section for another couple weeks, and this is my last official duty. I'm really happy to welcome you to this session where our new fellows have a chance to tell us either their latest, greatest work or what made them famous or anything else they'd like to say. This first session this morning focused a lot on atmospheric chemistry. This session is more focused on climate. I'd just like to remind you of a couple things. All the new fellows will be honored at the ceremony tonight, which I'd like to welcome you to come see them in tuxedos for maybe the first time in their life. And also the deadline for nominations for new fellows and for all other AGU awards is March 15th this next year. And so please think about nominating your colleagues. You don't have to be a fellow to submit a nomination, but we'd like to have a large list of potential new fellows to honor here next year. The first talk in this session is by Michael Mann.
Here. Okay, well, thanks very much, Alan, and I want to thank Alan for organizing this series. It's great to have an opportunity to speak in a forum like this. So I'm going to talk about the work that I've done using the paleoclimate record to try to learn something about the climate system. Most people probably aren't aware of the fact that my interest in climate proxy records like tree rings and corals and ice cores had nothing to do with climate change. I originally got interested in these sorts of data because I was, for my PhD research, investigating evidence for signals in the climate record associated with internal oscillations in the climate system. Things like El Nino on interannual timescales, but also evidence for decadal and multi-decadal cycles in the climate record. And one limitation we quickly came up upon was that the instrumental record isn't long enough to identify coherent multi-decadal cycles in the climate record. That's what got me interested in looking at proxy data. I ended up doing some work with Tom Delworth where we showed that unforced control simulations of the GFDL coupled model actually do produce a multi-decadal oscillation in the climate system that looks somewhat like what we see in the paleo record. It has a pattern emphasizing the North Atlantic ocean SST and sea level pressure responses that interact with the overturning meridional overturning circulation that give a sort of self-sustaining multi-decadal oscillation in the climate record. This actually got a name based on an interview that Dick Kerr did with me for Science about this work I was doing with Tom Delworth. I actually coined the term the Atlantic multi-decadal oscillation. It seems to have stuck. Sometimes, as I've said before, I think I created a monster. I don't think the AMO is responsible for nearly as much as has been attributed to it in some circles. Okay, but that was my interest in proxy data, was in learning something about climate dynamics. These are reconstructions that we subsequently did using proxy records like tree rings and corals and ice cores to reconstruct surface temperature patterns back in time. Primarily, my interest was in learning something about how El Nino had changed in the past and what relationship that might have with large explosive volcanic eruptions. What was going on with the North Atlantic oscillation? What could we learn about the dynamics of the climate system by extending the record back in time? Unfortunately, the one aspect of this work that by far got the most attention is actually the aspect of this work that I think in some respects is the least scientifically interesting. It's the boring thing that happens when you simply average over all of that interesting spatial variability that can teach us something about the dynamics of the climate system to get a single number for each year. The average temperature of, in this case, the northern hemisphere. This quickly took on a life of its own. It was called the hockey stick by my colleague, the former head of the Geophysical Fluid Dynamics Lab in Princeton. Jerry Malman coined the term the hockey stick to describe the temperature, the reconstruction of average temperatures over the northern hemisphere, which demonstrated that recent warming did appear to be unprecedented as far back as we could go. This became sort of an icon in the climate change debate when it was featured in the 2001 summary for policymakers. And whether I liked it or not, I was suddenly a figure in the climate change debate. I'm not going to talk about that here today. If you're interested in my story as a sort of accidental and reluctant figure in the climate change debate because of this curve we produced more than a decade ago, I've written a whole book on it, and that's all I'm going to say about that. What I'd really like to talk about here is what we can learn, once again, about the workings of the climate system from looking to the past, looking to past centuries, the past millennium or so. This is a study we published a few years back looking at the pattern of temperature change during the sort of low point of solar output, the period following the Maunder minimum back in the early 17th century, how surface temperatures appeared to respond to this lowering of solar irradiance based on empirical data, and what happens when you take a model like the GISS model, which actually resolves some of the interesting interactive ozone photochemistry that might be important in the dynamical response to changes in solar output, especially changes in ultraviolet radiation. And we showed that the model does yield something similar to what we see in the reconstructions. It appears that the dynamical response to this lowering of solar radiance leads to something akin to the negative phase of the NAO or the AO, if you like. Sort of interesting. This thing, you know, a lot of us are interested in this thing. There's reason to be interested in this thing, El Nino, La Nina, and so it has a profound impact on weather and climate around the world. It's arguably still the largest signal in the climate record, larger than even climate change itself, depending on the metric used to define that. And the unfortunate thing is that we still, and I think this will remain true with the publication of the next IPCC report, AR5, we still don't know exactly, in fact, we don't know very much at all what is going to happen to El Nino as a function of increasing greenhouse gas concentrations in response to anthropogenic forcing. Models still do not agree on how the dynamics that govern El Nino will respond, both in terms of the amplitude of variability, the size of individual events, and the overall mean state. So maybe we can learn something about that from the paleo record. And we published some work a few years back showing that the paleo record actually supports something that had been alluded to by Paul Handler back in the 1980s. There appears to be an El Nino-like response to very large tropical volcanic eruptions. That was always an enigmatic observation. I know folks like Alan were very skeptical about it for good reason. The result depended on a few, on the leverage of a few large events in the observational record. So what we decided to do was to go back in time and look at an independent interval using reconstructions of volcanic activity, reconstructions of El Nino from proxy data. And we saw that, in fact, that response held up. Subsequently, I explored this a little bit further with Mark Kane, Steve Zibiak, Amy Clement, where we took the Kane-Zibiak model of El Nino and forced it with estimated natural forcing, including volcanic forcing over the past 1,000 years. It's a little hard to see, but it actually reproduces that observation of an El Nino-like response in the first year or two following a large tropical eruption. And actually you see sort of like a damped oscillation thereafter, and there's even a hint of that in the paleo observations. This arises in this particular model from a very active dynamical response, the so-called tropical Pacific Ocean thermostat, a hypothesis originally put forward by Mark Kane and Amy Clement. On these timescales, in response to this forcing, it appears that the climate is in fact responding in a way that's consistent with the dynamical thermostat. Whether that applies to anthropogenic forcing or other climate forcings, of course, remains unclear. And it's possible that there are other explanations for that observation, but that observation does appear to be robust. We also showed that if we took estimated solar and volcanic radiative forcing over the past 1,000 years and drove the Kane-Zibiak model with those forcings, we reproduced coral observations of this sort of counterintuitive enigmatic El Nino-like anomaly during the Little Ice Age, a period that we think was cool globally, was actually more El Nino-like, warm in the eastern tropical Pacific. The medieval climate anomaly, sometimes called the medieval warm period, well, it doesn't look like it was a warm period in the tropical Pacific. It was actually a cold period based on these data. The model simulations reproduce that because ENSO is essentially under the dynamical thermostat responding oppositely to the imposed radiative forcing, a positive radiative forcing giving you a La Nina-like anomaly, just as a negative radiative forcing, like a large tropical eruption, giving you an El Nino-like anomaly. The y-axis is some sort of normalized anomaly in some scale I can't even remember. Sorry about that. We've gone on to do additional reconstructions with much expanded data sets, proxy data sets that extend back beyond the last 1,000 years, reproducing as best we can, or reconstructing as best we can the pattern of anomalies during the period we sort of think of as the medieval climate anomaly and the Little Ice Age. And to get away from the impact of the base period that's used to the modern base period, 1961 to 1990 in this case, to define those anomalies, we'll just difference the two. We'll just look at the pattern of the medieval period relative to the Little Ice Age, subtracting those two off. And that's what it looks like in our reconstructions. You see a couple interesting things. The warmest, the most positive anomalies are in continental regions of the northern hemisphere over North America and Eurasia, western Eurasia. You see that La Nina-like anomaly, the medieval period being more La Nina-like relative to the Little Ice Age. Again, somewhat counterintuitive. Counterintuitive enough that models don't reproduce that in general. Here are two different climate model simulations that we compared to the reconstructions. The first is the GISS Model E, coupled ocean atmosphere model, that actually has some of those important stratospheric interactive photochemistry that we think is important in understanding how the jet stream responds to a change in solar radiance. This other simulation, the NCAR CSM 1.4 coupled model, doesn't have that sort of doesn't have that sort of physics in it. And interestingly enough, it's only in the case of the GISS Model E where we see this pattern of enhanced anomalies in parts of the northern hemisphere continents that's somewhat like what we see in the reconstructions. In that model is coming from the fact that the medieval interval is in the relative positive phase of the AO or NAO pattern relative to the Little Ice Age. It's basically the flip side of what we saw before with the Little Ice Age. The NCAR model doesn't have that. Neither of these models reproduce a La Nina-like pattern in that difference. And whether that's because the models are missing some important physics that's behind that. These are two models, for example, that don't exhibit anything like the dynamical thermostat. There are some models within the CMIP-3 multi-model ensemble, and I believe the CMIP-5 multi-model ensemble, that do give that sort of response. But these are not two models that do, and consequently, they don't give a La Nina-like response. Maybe the reconstructions are wrong. The uncertainties are substantial. There are always potential biases in the proxy data. So this is still an interesting problem, and I'm not sure we have the final answer, but I think it's important to understand this because it does have deep implications. How El Nino responds to radiative forcing has very important implications for making regional projections of climate change under anthropogenic forcing and the reliability of those reconstructions. I've looked at applications to tropical cyclones. Sometimes it's fun to invent statistical models for predicting things like seasonal tropical cyclone counts. Students love to participate in contests using these sorts of models. And our statistical forecasts have actually held up pretty well against the other major groups that do this sort of thing. But what we decided to do was to extend the statistical model back in time using paleo reconstructions of the underlying climate indices that drive annual tropical cyclone counts in our model, reconstructions of tropical Atlantic sea surface temperatures of El Nino, a shorter reconstruction of the NAO, and we compared with sediment records of landfalling hurricanes. So both of these things now extend not just over the past century, but more than 1,000 years back in time. A statistical estimate of tropical cyclone activity based on a statistical model driven with climate indices, that's the blue, and the green is actual records of landfalling hurricanes from sediments along the U.S. East Coast, the Gulf Coast, and the Caribbean. And that's the comparison of the two. And they have some things in common, and they have some differences. How do we interpret those differences? Is one wrong? Are they both wrong? Are they measuring different things? We actually pursued that in some work that another undergraduate, Penn State undergraduate of mine did with me and Carrie Emanuel, where we took Carrie's downscaling scheme. You take large-scale atmospheric fields, you force a model of tropical cyclogenesis and tracking with those large-scale fields, and you can produce 1,000 years of synthetic hurricanes from a climate model. And we did that. And it turns out that if you look at overall basin-wide activity versus landfalling hurricanes, the two different things that those two different paleo estimates were measuring, the correlation you would expect between them at multi-decadal timescales is actually pretty close to the correlation that we saw with those two estimates. So maybe these two quantities, landfalling hurricanes versus basin-wide named storms, maybe the sampling statistics are such that they differ significantly, even on multi-decadal timescales. That could be important for understanding, the prospects for increased landfalling hurricanes in the future, for example. We've done applications to semi-empirical modeling of sea level, something I'm involved now, which I'm very excited about with Ryan Shriver, Klaus Keller, and Axel Timmerman. It's sort of like the climateprediction.net experiments. You assimilate paleo data into climate models to try to constrain parameters. I see I'm running short on time, so let me talk just about one more aspect of estimating climate parameters from paleo data. One of the things that we try to do with hemispheric temperature reconstructions and comparing them with models is to see if we can get independent constraint on the equilibrium climate sensitivity. And there was a study published a few years ago by Gabi Hegerl that showed that the paleo reconstructions actually suggest a somewhat low-end sensitivity of about 2 degrees C versus the typical sort of 3 degrees C mid-range CO2 doubling sensitivity. We've actually looked at one factor we think might explain that. We think the climate sensitivity might be underestimated by these sorts of experiments because some of the large forcing events may be underestimated in the paleo reconstructions. And we published a paper earlier this year where we used a simple model of tree growth forced by a GCM simulation. That simulation is red. An actual tree ring reconstruction of temperatures, blue. And you can see it greatly underestimates the expected cooling in response to the largest volcanic eruptions of the past 1,000 years. We argue that may be because of threshold responses. The trees at tree line can no longer record cooling beyond a certain amount. They're basically dormant for the season. You can actually induce chronological errors when you're missing rings and you start averaging records from different regions that are missing different years. My good friends who I greatly respect and value their contributions in the tree ring community tell me there's no way that this could be happening, that they cross-date these trees, et cetera. They almost had me convinced that we were wrong, and we've had a comment reply recently about this. But the instrumental record really does, that is available, really does suggest that 1816 was a year without a summer, as the model suggests. It wasn't the year that is slightly warmer than the previous year, which is what the trees would suggest, in which we reproduce because of these effects that I talked about when we simulate the tree response. One of the criticisms that they have made about this hypothesis is there's no evidence that this is actually happening in the underlying tree ring data themselves. Well, we've looked at that now, and I'll just touch on that slightly. We've taken the prediction from our original simulations of the timing and probability of missing rings, regional probability, based on the response to the very large cooling events associated with the largest eruptions, where we estimate a more than 80% probability of a missing ring in 1258 in a given region and roughly 50% in 1816. And so we've taken that probability distribution and we've applied it to the raw tree ring chronologies that underlie the Dorigo et al. Reconstruction that we were comparing with. And what we find in the surrogates, in these Monte Carlo surrogates, where you allow for the potential of missing rings and you produce a large realization of possible variance on the raw composite that take into account the predicted cooling errors. And suddenly you see, for example, that a lot of the surrogates really do want to cool quite a bit in 1258 when the model says they should be cooling. And they don't produce this odd cooling 4 years later that our original analysis predicted as a response of these chronological errors. They cool at the right time, not quite as much as the simulation, but certainly now there's a pronounced 1258 cooling, which we would expect. And now the trees do produce a year without a summer rather than a year with a slightly warmer summer. And in fact, some of the tree surrogates overlie almost perfectly the instrumental Berkeley temperature record for that year. So we think there is some empirical support. I'm going to wrap it up because I can see Alan wants me to. Talked a little bit about some work that we're doing in seeing the impact that this may be having. And finally, if I can take just another 30 seconds, we've addressed another issue that's been raised recently. There was a paper in Nature Geoscience earlier this year that suggested that tree ring reconstructions of temperature may be losing long-term sort of millennial scale trends because of some of the limitations in the time scales that they can record, and that this could influence other proxy reconstructions. The lead author, Jan Esper, actually issued a press release claiming that this undermined the conclusions of the last IPCC report. So we decided, well, if that's true, maybe we should look into this. With this recent analysis we've done, where we've estimated the fingerprints of all the forcings, including orbital forcing, in actual proxy data, we removed that and we looked at the residual variability, which in principle would be unforced or internal variability. And if Esper et al. Are correct that reconstructions, multi-proxy reconstructions, are underestimating the warmth of the medieval period because of this effect, then that trend in the residuals should be positive. And instead, it's actually negative in all of the proxy reconstructions. In fact, it's most negative in Mann et al. 2009, meaning that it appears that we are guilty of having overestimated the warmth of the medieval period in our reconstruction, if other reconstructions are correct. Only two reconstructions, the two pure tree ring reconstructions of Dorigo et al. And Frank et al., which is actually Esper's group, show a positive trend, indicating that maybe in those reconstructions there is an underestimation of the long-term millennial scale trend. There is an underestimation of medieval warmth because of some of the factors that Esper talked about. And the last thing I will comment on...
Much more than 50.
This is it. This is it. So that's the internal variability we diagnose in those studies. The red is the actual trend over the past century. It's not consistent with internal variability, best as we can estimate it from these reconstructions. Thank you.
Thanks very much. Believe it or not, we do have time for a couple questions. Kevin.
Sure. Sure. Yeah, I agree. Yeah, there's a difference between looking at, say, the gradient in sea surface temperature across the Indo-Pacific and looking at, what we think of more generally as ENSO, including the large-scale teleconnections and the influence on rainfall and atmospheric circulation. There isn't a perfect one-to-one correspondence because there are thresholds that are involved. There are nonlinearities. So if you uniformly warm the tropical Pacific, even if you keep the same east-west anomaly pattern, you can actually get a different teleconnection. And so I think what Kevin is alluding to is that we have to think carefully about the distinction between some simple metric like Niño 3 or some sort of SST gradient across the tropical Pacific and the more general sort of ENSO phenomenon that's often of interest.
Okay. Thanks very much. Congratulations. Our next speaker is Ron Stauffer from GFDL. Oh, you get there on Stauffer, right? Sorry.
No, you got it right. Okay. Thank you, Alan. Thank you all for being here. It's quite an honor. I'm going to take a different tact that Mike just took. He reviewed a lot of his research. I'm going to just talk about the latest research that we've been doing at GFDL with our Earth system model. And I'll be discussing the role of land use changes in the 20th century. So this is what I'm going to hope to convince you of in the next 15 to 20 minutes, is that Earth system models can be used to understanding the past carbon changes. CO2 fertilization played an important role in the 20th century carbon fluxes. I'm going to assert, but not really prove, that CO2 fertilization impact in the future is highly uncertain. Historic land use carbon changes have increased the current CO2 concentration, and the secondary vegetation is the largest sink of carbon both historically and in the future. This is a cartoon of the type of model I'll be talking about. The top panel shows a climate model typical of AR4, the last IPCC, where you have general circulation models of the atmosphere, the ocean, and land and sea ice coupled together. And when I talk about an Earth system model, what I'm going to be discussing is adding in the green boxes, which add the ocean and land ecology and biogeochemistry components and a part of the atmosphere to keep track of the CO2. And there's obviously many other definitions of an Earth system model possible, but this, when I'm using it, this is what I'm talking about. For the modeling geeks in the audience, these are the details. The atmosphere and the sea ice components are very, very similar to our AR4 model, CM 2.1. It's a 2-degree or 200-kilometer atmospheric model with 24 vertical levels. We actually built 2 ESMs with 2 different ocean component models. In one, we have something that's called MOM-base, which is a Z or depth coordinate with 50 vertical levels. In the other, we call GOLD, or ESM2G, which has density as its vertical coordinate, and it has 63 levels, and both those models use a 1-degree or 100-kilometer grid, tripolar grid. And I'll be talking about a new land component model also, which is on the same grid as the atmosphere. And just a little bit more about the 2 ocean models. What you see is layers in the ocean represented by various colors, and these are density in the vertical. So when you map that onto a Z-coordinate grid, it looks kind of like this, where the boxes are very regularly spaced. In a density, the interfaces follow the density levels. The model on the left is the type of model we've been using in this community for the last 40 years or so. We have lots and lots of experience with it. Model on the right is much newer, and the real advantage of this model, in my opinion, is that you can really explicitly control your dipycnal, or the mixing between density levels in the ocean in these models. And so there's no numerical dipycnal mixing. The way this model is forced, we use estimates of the historical estimates of the natural forcings, both solar and volcanoes, of greenhouse gases, and I'll be talking about 2 different kinds of runs. In one, the CO2 concentration is given to the model. In the other, the CO2 emission is given to the model, and it predicts its own concentrations. Also, aerosols, sulfate dust, black carbon, organic carbon, and various other aerosols are given to the model. And it's run from 1861 up to 2005 that way. And our model in particular, since it predicts the ages of the forest and the age structure of the forest, we need to initialize the land carbon stores, both above ground and below ground, at 1861. And the way we did that, if we branched the runoff of the control at an arbitrary point and imposed a land use scenario from 1700 up to 1861 to try to get those land carbon stores about right. Of course, in the middle and high latitudes, the soil carbon's not equilibrated in 150 years, but you can read about that in a paper by Sentman et al. Just exactly how we did it and how we tested and how we chose that period. But the bottom line is it's a combination of the practical matter of CPU time versus trying to get the model more equilibrated. I'm only going to show one picture of the physical climate system, and this is it. This is global mean surface air temperature. The black line are the observations from 1860 up to about present day. The green lines are from ESM2G. The red lines are from ESM2M. The solid ones are when you force the model with concentrations, the historical estimates of the concentrations. The dashed lines are when you force the model with the emissions. And you can see that all of those forcings kind of capture this flat up of the historical record. Of course, you wouldn't expect the wiggles to match since the model's starting from arbitrarily different places in the control run. So the rest of the time, I'll be talking about carbon stuff. So in the land model, each grid cell has a number of tiles, and those tiles can consist of the following types of things. The first one is forests that have never been cut, or primary forests or all managed forests. They're called different things by different people. But these are forests that humans have never cut down anywhere in the history. There's tiles that simulate crops and pastures. And then there's also a number of tiles where once humans have cut down the trees, for whatever reason, they abandoned those areas and let the forest regrow. And so you can have a whole series of secondary forest tiles with different ages of trees in them. So this land model unique features is that we do wood harvesting of both the primary and the secondary forests. I've already talked about the ages of the forest and shifting cultivation. And something else that's different about this model is that each of these tiles has its own below ground component to it. We don't average them together for one big over a whole grid box. The vegetation structure of the model is the classic kind of big leaf thing. We have 5 vegetation types. The model predicts its own vegetation from the climate that the model is producing, which can create problems. If you have a bad climate simulation, you will not have forests where you want them to be. There's 5 vegetation carbon pools. There's 2 soil carbon pools, a fast and a slow. There's 4 different land use types. And we have a natural mortality and a very simple fire model that's included in this model. So now looking at some results. The picture on the left is from the IPCC, and in it you can see estimates of the historical emissions from 1860 up to about year 2000. For the human part is this dark green, or burning of fossil fuels and whatnot. The dark brown is the accumulation of carbon in the atmosphere. The lighter brown is accumulation of carbon in the ocean. And the 2 shades near the 0 line are the net land flux, if you would add them together. And they split them out into 2 parts. One is what they call a land use flux, which is kind of this light green here. And a light or yellow color is what is everything else that's coming off the land. If you look at the picture on the right over here, I've reproduced the solid line from Houghton et al., which is this land use flux. And when we force the model the same way that that line was determined, which assumes no changes in climate and no CO2 fertilization, our model does a fairly good job of capturing that trend over the last 150 years or so. You can see that about the middle of the 1900s, there is an overestimate by the model relative to Houghton's estimates. And that might be a function of the input scenario, and I'll talk a little bit more about that coming. And so what I've tried to do and evaluate how the model's performing is to follow an example that Tons did with the observations, and assuming a very simple global box model, where the changes in the atmosphere are equal to the changes of the fluxes coming out of the land, both the human fossil fuel emissions and the other land carbon fluxes, and the oceanic carbon uptake. And so what I'm going to do now is go through and compare the model to these TONS estimates one by one. So for the first one, look at the atmospheric PCO2. The black line is observations. The red and the green are the two different models. Again, from 1860 up to present day, you can see the models are about 20 ppm high around present day. If you then compare them to an one of the RCP, which is a future scenario, runs, this happens to be RCP 8.5, which comes out of a very simple model. The RESM is about 70 ppm higher by 2100 than the simple models estimates coming out of RCP 8.5. But I'm going to just focus on this historical period for the rest of this. So converting those atmospheric PCO2s into carbon inventory changes, the black line again is the observations. The red and the green are two different models, and you can see the split here in the middle of around 1950 or so. And you can see that the models are 5 to 10 petagrams of carbon too high by present day, which we took as being pretty good. Now looking at the ocean changes, again, the black line is from TONS, which is based somewhat on model results and on observations. The red and the green lines are from the models. I've included the Sabine estimates for the 1994, I believe, where the central estimates here and the uncertainty is represented by the two triangles. And you can see that the models and then the TONS estimate all goes through the Sabine uncertainty range. Now looking at the land, the first thing that struck me when I started looking at the carbon was something that I didn't know, which was the land flux. This is the cumulative change in the land carbon fluxes into the atmosphere. The solid line is the land carbon fluxes. The dashed line are the fossil fuel and cement emissions. The thing that surprised me was that most of the carbon in the atmosphere, due to human activities by the middle of, say, 1950, was actually coming out of the land, not from the burning of fossil fuel. That was something I hadn't realized. And you can see that the models don't get this change of sign in the fluxes until around 1970. It's a little bit later than the observations. I just put the Sabine estimates, doing the same game, assuming a simple box model, putting Sabine's estimate for the land, for the ocean, over onto the land plot. You can see that ESM2G kind of goes through the uncertainty in, bars, and ESM2M, again, is a little bit too high. The question is, okay, that's good for the GFDL model, but what about the other models? So this picture shows the GFDL ESM2G is now in red, and results from IROC, MPI, IPSL, and the Canadian model. And you can see there's a lot of uncertainty. All the models kind of capture this notion of that the land was a source of carbon up to about 1940 or so, and then it became a sink. And you can see that they all missed the timing of the change relative to the TONS estimates here in the middle, 1950 to 1960 or so. And it looks to us like it's from the scenario. If you, the pictures on the left are the area by land use category. This is the primary. This blue line here is from pastures. And these are the carbon fluxes from all those different components. And again, you see this big spike in the middle is from the pastures in particular. And we think that that blip is being caused by the pasture changes, and we're talking to the folks that generated the land use scenario to give us another land use scenario that has a different assumption about this time. And you can also notice that the secondary forests are the biggest carbon sink through the historical period.
Pastures is cows?
Pastures are the lands that are used for cows or goats or whatever. So the red line here is the SM2G force way I've been discussing it. The light blue line is the tons et al. If you, in the model world, you can make a run where you assume no land use, and that's the blue line. So if you compare the blue to the red, you can see that the land use has added about 30 to 40 parts per million of carbon by 2005. You can also do another kind of game in the model where you assume absolutely no CO2 fertilization, and that's this kind of purplish line. And you can see that the enhanced growth due to CO2 fertilization has been a large negative feedback on the current climate by the trees taking up enough carbon to lower the PCO2 by about, say, 80 ppm. In the future, how do these things change? One of the things you would notice from the land use scenarios in the future is that actually the land use scenarios and all the RCPs are fairly common to each other. If you look at 6, 4.5, or 8.5, and just focus on this black line, the land is simulated to stay a sink of carbon into the future, but this would be highly dependent on your assumptions about the exact land use scenario and if the CO2 fertilization would continue to be a primary factor and not be limited by nutrients of some sort. So to conclude, hopefully I've demonstrated the Earth system models can be used to understand past carbon changes. CO2 fertilization played an important role in the 20th century carbon fluxes. The historic land use carbon changes have increased the current CO2 concentration, and the secondary vegetation is the largest sink of carbon both historically and in the future. Thank you.
Thanks very much. Do we have questions? David? Repeat the question.
Okay. The question is the 80 ppm due to CO2 fertilization supported by observations? And I am not an expert. I'm a novice in this field at this point. My understanding is that the observations are argued about at this point. It's not a settled issue. So the question is, if we use oxygen as a tracer, a la Keeling's suggestions, could we determine the carbon fluxes better between the land and the ocean? Is that a fair rendition of your question? And so the short answer is no, we haven't put it into our model. We have talked about it, and I don't know if anybody else has put it into their model or not. But it is an interesting idea to do.
Thanks very much.
Thank you.
Thanks very much. Our next talk is by Cora Randall from the University of Colorado. Hi. Just go forward and backward.
Okay, so we're going to move up to the middle atmosphere now. I'm going to be talking about coupling that is triggered by energetic particle precipitation. And first, I'd like to thank the many people who have been involved in this work with me over the years, and the people who are highlighted in yellow are the people who contributed in particular to the work that I'll talk about at the end of this talk. Just a general outline. I'll give a little introduction to the concepts that I'm talking about, show you some of the measurements that have been made, the chemistry climate model simulations, and then a short summary, talk about a few of the outstanding issues. Okay, so throughout the talk, I'm going to be talking about energetic particle precipitation. So it's the process by which charged particles, electrons and protons from the sun or magnetosphere, enter the Earth's atmosphere along the magnetic field lines, generally in the polar region. And I will abbreviate that with EPP. Okay, so the basic idea here is we're trying to look at the potential for EPP to trigger coupling in the atmosphere. So we're asking, to what extent do the changes in polar ozone that are caused by EPP trigger a redistribution of the solar and magnetospheric energy? And the way that this might happen is the energetic particles will come into the atmosphere. They change NOx, odd nitrogen, which can affect ozone, and then the ozone can, because it's radiatively active and it would be affected in the polar regions, can change the temperature, latitudinal gradient of temperature in the atmosphere. That then could change the winds, that would change wave filtering, and then you would have an effect on the circulation that would have possibly some feedbacks. So the basic idea of the energetic particle precipitation is sketched here, where this is ionization rate versus altitude. And what I'm really focusing on in this work are the effects of auroral electrons, which deposit their energy in the lower thermosphere, the medium and high energy electrons, which deposit their energy in the mesosphere, and then the solar protons, which can penetrate all the way down to the stratosphere. So the basic process is that you have the charged particles come into the atmosphere. They cause ionization and dissociation of the molecules, and then for instance, the N2 will combine with O to create NOx. In this talk, I'm considering NOx to be NO plus NO2. We also get HOX created. That's a short-lived species, so I'm not going to be focusing on that. The reasons these are important, though, is because they are involved in catalytic cycles of ozone depletion, depleting ozone, as well as interfering with some of the other catalytic cycles. Okay, so we're going to talk a little bit about a couple of the effects that we define for energetic particles depending on the energy of the particles. Higher energy particles can penetrate farther into the atmosphere. So we have what's called a direct effect, and I'm talking about these effects on the stratosphere. So the direct effect of energetic particle precipitation on the stratosphere is for the high energy particles to penetrate directly to the stratosphere, where they create NO right there, and that NO is then available to participate in ozone reactions. This does not happen very often. It's typically, we're talking about something like a solar proton event. Even though I wrote electron up there, it could be electrons or protons. The other effect, which occurs routinely, or has the potential to occur routinely, is the indirect effect, where you have lower energy electrons. They will deposit their energy in the lower thermosphere, maybe the uppermost mesosphere, but generally the lower thermosphere, so we're talking something like auroral electrons. And then this NO can descend during the polar winter, when the circulation is such that you would actually have descent in the atmosphere, until it reaches the stratosphere, where then it would participate in the ozone reactions. Okay, this indirect effect requires very efficient downward transport during the polar night. And the reason is that the odd nitrogen lifetime in sunlight is very short in the upper atmosphere. So if you get into the upper mesosphere or lower thermosphere, you're talking a lifetime of days or even less. And therefore, you need to have efficient transport in order to get the NOx down into the stratosphere. Once you get it down into the stratosphere, then the lifetime is much longer. Because you need this efficient transport, it's going to be influenced very heavily by dynamics. So things like the stability and strength of the polar vortex, which is what this depicts here, the amount of descent in the mesosphere itself. Okay, the indirect effect was actually first simulated by Susan Solomon along with Paul Crutzen and Ray Roble in a 2D model. They published their work in 1982. And what they wrote was that substantial amounts of NO produced in the thermosphere can reach the stratosphere, particularly at high latitudes during polar winter. This process provides a coupling between the upper and lower atmosphere, which may play a significant role in the photochemistry of odd nitrogen and odd oxygen in the stratosphere. I think they were spot on with that, and this process was confirmed a couple years later in a publication written by Jim Russell in 1984. Where they were showing observations from the LIMS satellite instrument. This is the LIM infrared monitor of the stratosphere. It was an infrared instrument that measured during the polar night. And what this plot here shows is LIMS NO2, poleward of 75 degrees north, during the 1978 to 1979 winter. as a function of altitude. And you can see this tongue of NO2 coming down throughout the winter. This was very easily attributed to EPP because the only source of NO2 at these altitudes in this time of year and latitudes is EPP. Okay, in the next couple decades, there were actually not very many observations of the EPP indirect effect. There were some. They were not ideal. Mostly they came from the solar occultation instruments, SAGE, HALO, and POEM. These instruments, of course, they require sunlight, so they're not able to see the polar night. Nevertheless, there was enough data that we were able to quantify the amount of NOx coming from EPP, or EPP NOx, that descended into the stratosphere. And basically, we calculated that EPP yielded up to about 10% of the total NOI in the southern hemisphere stratosphere, or about 40% of the polar NOI in the southern hemisphere stratosphere. There was less in the northern hemisphere. We did not have good evidence that this was occurring routinely in the northern hemisphere. In 2003 and 2004, a lot more NOx data became available with these satellite instruments here. And so what this shows you is just an example of some of that more recent data. So on the left-hand panel, I have northern hemisphere polar NOx from the ACE FTS instrument. This is also solar occultation, so it doesn't get the night. However, it has an orbit so that it is in the polar latitudes for many months out of the year, and it measures both NO and NO2, which means that we can get NOx measurements from the stratosphere all the way up into the lower thermosphere. On the right-hand side is also the ACE data in the southern hemisphere. What I want to draw your attention to is, well, first of all, these plots are for different years, 2004, 2005, various years up to 2012, slightly different years in the southern hemisphere. But the thing to look at here are these tongues of NOx that are coming down in the atmosphere that you can see coming down here. Okay, you see the same thing in the southern hemisphere. It happens really all the time, but not as intense in the southern hemisphere during these years than in the northern hemisphere. This was very different from what we were finding from the previous decades. We believe that what is causing this is dynamical phenomena, so that in these years 4, 6, and 9, we had some very unusual meteorology where we had extraordinary stratospheric warmings with these remarkable recoveries. Gloria Manny has written about these. And during the recovery, we had very much enhanced descent in the mesosphere. So even though, for instance, in 06 and 09, there actually was very low energetic particle activity because it was right at solar minimum, we actually were able to bring down a significant amount of NOx simply because there was so much descent in the mesosphere. In 2012, we haven't finished analyzing this completely, but you can see that these dashed lines, there were some solar proton events, and that definitely enhanced the amount of NOx that was coming down. But the point to take away here really is that in both hemispheres, we do see the NOx coming down to the stratosphere. Okay, the largest indirect effect that we have seen so far occurred in the Arctic Spring of 2004. This data shows this. This is from the HALO instrument. I'm plotting here NOx on the top, ozone on the bottom, versus time throughout the year. The blue points are all the data from 1991 to 2003. The red points were in 2004, and this is all at 40 kilometers. You can see the large enhancement in NOx in April of 2004, the large decrease in ozone. We had about a factor of 4 increase in NOx, 60% decrease in ozone. Okay, in terms of the column ozone, this was not a significant effect. It changed the column ozone by about 1%, or 3 Dobson units. But there was obviously a huge local effect, and that's what we want to probe is, can this local effect actually be felt in other regions of the atmosphere? The reason this year was so big was both because of the favorable dynamics that I was telling you about on the last slide, and also because this happened to occur closer to solar maximum on the descending phase when there was elevated particles. No solar proton events that affected this, but more auroral precipitation. Okay, so the question we want to ask is, do these effects on ozone lead to coupling? So again, you'd have the energetic particles coming in, creating NOx. This would interfere with the processes controlling ozone and then go through this temperature, winds, and waves. Because that's hard to actually observe directly, we're using the WACCM Whole Atmosphere Community Climate Model from NCAR in order to look at these processes. So WACM is a high-top chemistry climate model, so it goes from the surface to about 150 kilometers. Very important point is that it does have a detailed ozone chemistry in it, including the catalytic cycles and the heterogeneous chemistry. It also has the, because it goes up into the thermosphere, the ion chemistry, meaning the aurora and solar proton events, although the models that I'm going to show you did not have solar proton events in them. And it parameterizes the gravity wave drag, where the gravity waves are generated by orography fronts and convection. And the other thing is it can be run in either an interactive mode or a specified meteorology mode. Specified meteorology meaning that you actually could compare on a day-to-day basis with measurements. The interactive really is just free-running meteorology, and I'm going to show you results just from free-running WACM. Okay, so what we did is we ran two simulations, one with auroral electrons and the other without auroral electrons. So these are just low-energy electrons depositing their energy in the lower thermosphere. Each of the runs was 40 years long, and we just repeated 1 year after another. Free running, the AP index, a measure of geomagnetic activity, was 27, which means that it was a moderately high level of geomagnetic activity or auroral precipitation in the run with the aurora, but it was only slightly higher than what really pertained during the Southern Hemisphere winter of 2003. So we're comparing the results to the MEPAS data from 2003. So what I'm showing here is the NOx from MEPAS in the polar region as a function of time and pressure, and compared to that is the average of the 40 years of the WACM run. And you can see that qualitatively the WACM run really does a very good job capturing the NOx coming down. However, you will also notice that there's an underestimate of NOx in WACM compared to MEPAS. That's probably, at least in part, because we do not have the medium or higher energy electrons in here. There were a few very, very small solar proton events, but it probably would not have affected this to any significant extent. The other thing that might be a little bit harder to see is that the WACM NOx descends a little bit later in time than MEPAS, so there will be some differences for sure. But the take-home message here is that the agreement is good enough that we felt that it was appropriate to look further at the WACM model to try and understand these further effects and that might show coupling. Okay, and so what we're doing here is I'm showing the difference between the WACM run with auroral electrons and without auroral electrons at 80 degrees south, and this is a function of time and altitude here, or pressure. The unshaded regions are significant at the 95% confidence level. So I take with, minus without aurora, and this is ozone here that we're talking about. So first you can see what we've already mentioned, that you get this NOx-induced ozone loss here. And the signal persists throughout the next year, so through the, into the summer, and actually through the summer into the next winter. That's probably because the air is just, with the low ozone, is confined to the polar region to some extent. Not completely. You can see that there's not as much a depletion of ozone there as there was originally. And then this other feature you can see is that we get an increase in ozone in December in the lower stratosphere. And while I'm not showing all of the backup for that, you can see from the model that that's because the NOx is tying up CLO. So we're actually mitigating the ozone hole here. You got the NOx coming down from the EPP. It added some NO2 to the lower stratosphere, which then tied up the CLO and prevented it from depleting ozone. And it turns out that's actually where the coupling that I'm going to show you comes from. So here what I've done is I've blown up that last figure just for November through January, and here is the increase in ozone that I showed you. And here is an accompanying increase in temperature. You had more ozone, therefore more heating from the absorption of UV light, because we're now, of course, looking at the summer here. Okay, so you got heating at the pole. That did give you the temperature gradient that you would expect. Higher temperatures at the high latitudes going to no signal down at the lower latitudes. That caused a change in the geopotential height of the latitude surface of the pressure surfaces in the polar region. And because you had that change in gradient, then you're also then getting a change in the zonal mean, zonal wind. These are monthly averages that I'm talking about here. So this was an effect that occurred significantly enough that you could actually see it in a December monthly average. So you get this change in the zonal mean, zonal wind here in December. It's in the direction such that it's more easterly here, which means that it's more summer-like conditions. So the EPP has caused the stratosphere, to become more summer-like than it would have without the EPP. And summer-like conditions mean that because the middle mesosphere is controlled by largely, the residual circulation, where you have ascending air and cooling in the mesosphere. This is because of the gravity wave forcing. You also see in Wacom that you're getting cooling. This is the December change in temperature. You're getting cooling here in the mesosphere. Possible implications for PMCs, because, meaning polar mesospheric clouds, because polar mesospheric clouds, of course, need these cold temperatures in order to form. Okay, so this is the basic mechanism then, just to summarize. Basically what you do is you have EPP that happens in the southern hemisphere winter. That creates NOx. The NOx descends into the stratosphere. It ties up CLO, mitigating the ozone hole. Because you have more ozone than you would have, you get heating in the summer polar lower stratosphere, a shift in the zonal wind. That changes the gravity wave filter, and you get more upwelling and cooling in the mesosphere. So you basically go from the southern hemisphere winter all the way down to the lower stratosphere, back up to the mesosphere in the summer. In Wacom, this only happens in the southern hemisphere. Okay, so some caveats, meaning we didn't see anything in the northern hemisphere in terms of coupling. The Wacom southern hemisphere vortex persists too long, so this is probably an overemphasis, an exaggeration of the effects. On the other hand, in the northern hemisphere, the vortex is too small. Therefore, it's probably an underestimate of what would have happened in the north. And the other point is that we didn't account for any higher energy electrons, so they certainly would have added something. So finally then, just some outstanding issues. We always have to worry about the fidelity of the dynamics in the CCMs, the gravity wave parameterization in particular. Like I just said, we have this missing electrons with a higher energy, which would deposit their energy lower and therefore get down, the NOx would get down a little bit more easily. We really need observations of polar night, and there are few that people have been able to get out of their retrievals, but their instruments were not planned for that, and so we really don't have a continuous record. This is in the up through the mesosphere and lower thermosphere. We need winds in the mesosphere above the stratopause in order to understand the transport up there. I think most people here would agree, we need continuing observations of the stratosphere. Ozone isn't totally a solved problem. And we need to understand this unusual meteorology that we've been seeing in the northern hemisphere in the last decade or so. So thank you very much.
Thanks very much. We have time for some questions. Yes.
Are we able to actually see the enhancements of the PMCs that actually show up?
Could you please repeat the question?
Yeah, so John's asking whether or not we could actually see the enhancement in the PMCs. Did it actually show up? So in the model, this version of the model did not have PMCs in it, so I couldn't look in the model. All I could see was the temperature decrease. In reality, we're actually just starting to look at that, so I haven't actually gone through all of the years and correlated, PMCs to energetic particle activity. Of course, there's so many other things that control the PMCs, it'll actually be difficult to do that. But I can say that we have noticed these teleconnections between the winds in the southern hemisphere, lower stratosphere, and the amount of clouds, PMCs, that we observe in December or at the beginning of the season. And we've published that work with Bodil Carlson, was the lead on that. So this kind of thing, this kind of coupling does happen. Whether or not it's triggered by EPP, we haven't confirmed that in the observations yet.
Any more questions? Yeah, thank you very much. Congratulations. Our next talk is by Daniel Murphy. You might have noticed we've organized this by starting on the East Coast, going to Colorado, and the last one is from California. Oh, whoops. What did I do? So you can forward and go back.
Yeah. Okay. I can see that. I can sort of hear some people here have read the, what was in Nature in 1964 after the first U-2 flights into the stratosphere that were, I think, non-classified and available. So I'm going to talk about the chemical composition of stratospheric aerosol particles. And it's sort of a nice story that we have some old information and some things that are very new. We've known for many years that the stratospheric aerosols are mostly sulfuric acid. that comes from oxidation of carbonyl sulfide and to a lesser extent sulfur dioxide that get into the stratosphere. They oxidize, form sulfuric acid. Some of the newer results I'm going to talk about are how you can classify stratospheric particles into three types, what the stratosphere teaches us about organic aerosols, and something about the phase, meaning liquid or solid, of the stratospheric aerosol. So some of the dates sort of from my research here in the 1985, you had the ozone hole, and the research then was showing that heterogeneous chemistry is very important. But at the time, there was little data on the aerosol composition besides it being mostly sulfate, and it sort of bothered me that people had all this heterogeneous chemistry, but on sulfuric acid in the lab, they were applying it to the stratosphere, and there weren't any good measurements of what was in the stratosphere. And I started building the instrument, the Palms instrument. Because of that, I started with some preliminary experiments in Murray Johnston's lab, and instrument made ground-based measurements in 1993 and did its first science flights on the WB-57 in 1998, where it flies in the nose of the airplane right up there and sort of occupies the entire nose of the airplane. And the way the instrument works is that you bring air in through an inlet and it goes into the instrument, and one of the things that happens is it crosses a continuous laser beam. And you have to have this because you don't know ahead of time when a particle is going to go into the instrument. So the first thing you have to know is when has a particle gone into the instrument, and then you quick fire an excimer laser and hit that particle with a pulse of laser light from the excimer particle. You blow it apart, you hit it really hard and form ions, and you analyze those positive or negative ions with a time-of-flight mass spectrometer. And you can do this in a size range between about 1/4 of a micron up to much bigger particles. And one of the things here is that this size range includes for the stratosphere most of the mass, most of the light scattering, but not necessarily the majority by number of the particles there. So a good number of smaller particles that we're just sort of blind to. So I said there are three types that describe most of the stratospheric particles, and this is type 1. This is sulfuric acid with metals. So most of the sulfuric acid particles that we measured in the stratosphere have some metals. So you see here, you see iron, magnesium, potassium, nickel, you see iron hydrates. The iron peak is the largest in the spectrum. That's because we're looking at the positive ions. In fact, this particle is mostly sulfuric acid. You can see this from this peak here, protonated sulfuric acid. Basic chemistry, it's really hard to protonate sulfuric acid, so you get a very, very small peak representing a lot of sulfuric acid, whereas iron forms a positive ion very easily. So in fact, this is a small amount of iron in sulfuric acid. You look at the vertical profile of these particles relative to the altitude of the tropopause, they're clearly a stratospheric particle type. You don't see these particles very often in the troposphere. So these are being formed in the stratosphere. But where are the metals coming from? And we can get a clue by looking at the ratio of some of the metals. So here I've pulled out the ratio of potassium to iron histograms, particles measured above 17 kilometers in the stratosphere and below 12 kilometers in the troposphere, and you see very different histograms. A very narrow histogram with a lot less potassium in the stratosphere. And if you put on the average composition of the Earth's crust here and the average composition of meteorites here, you can see that the potassium up here is coming from meteorites, whereas down here there's a broad range because there's different minerals, but it's coming from the Earth's crust. And it's not only potassium, but all these metals actually match the meteoric ratios. So we know that these metals in the stratospheric particles are coming from meteors. And one sort of incredible thing to me when I worked out the math is that this potassium that we're measuring so lightly is 1 ton per year over the entire Earth coming in, and we can measure it. And a lot of that is because it's in the particle phase in the stratosphere, which is a part per billion to start with. So you have this huge enrichment into the particle phase. So the mechanism here is that the meteors come in, they ablate above 80 kilometers. When a meteor ablates, it evaporates, you have gas phase iron. Gas phase iron is not going to stay in the gas phase very long. It's going to recondense into nanoparticles. Those get transported down mostly over the winter poles, as in the last talk, and there's a lot of coagulation, so you have many nanoparticles per lower stratospheric particle. And as sort of a sidelight, you can do lab calibrations on our mass spectra, And to the extent we understand the sulfur cycle, if you can do lab calibrations on the relative iron and sulfur peaks, you can constrain the flux of meteors. And we found an estimate that was consistent with previous estimates, but actually ruled out, it actually narrows the range. It actually rules out some of the high-end estimates of the flux of meteors into the Earth's atmosphere. Most of these meteors, incidentally, are very small. The main flux is in very small ones. But there's another mode of sulfuric acid particles. So if you look at sulfuric acid particles above the 17 kilometers in the stratosphere, and you look, mass 56, this is iron. You look at the size of the iron peak, you see this peak, these are the particles with metals. Then you see these other peaks that don't have iron, and the distribution is bimodal. This is not a continuum. In the troposphere, you see all these places, you see this continuum between organics and sulfates and different kinds of organics. This is clearly bimodal. There are two distinct source regions of sulfuric acid particles in the troposphere. And if you look at a mass spectra from one of these, again, this is where the iron peak would be. We have a signal to noise of 1,000 or 10,000, and it's not there. So it's not that there isn't just a little bit of iron, there's none. And these particles also are formed in the stratosphere. They have a profile in the stratosphere. Another thing I'm going to look at in comparison to the next particle type is you look at the size of these carbon and sulfur peaks. The carbon and sulfur peaks in these particles are similar in height. It turns out, as I said before, sulfuric acid doesn't like to form positive ions. Carbon, it turns out, is coming from much bigger organic molecules that were blowing all the way down into carbon. And we're much more sensitive to it. So the fact that these peaks are similar means the particles are on order of 1% carbon. And then you can go to the next kind of particle type, which is I call an organic sulfate mixture. And here, the carbon peak is 100 times larger than the sulfur peak, which means that we have probably more carbon than sulfur in this particle. And these particles are coming from the upper troposphere. You look at the vertical profile, and they're going up into the stratosphere. But these particles, these mixed particles, are 60–80% of the particles in the upper troposphere, and these are the ones that are getting transported into the stratosphere, whether it be through the tropics or through mid-latitude folding events or whatever. So this is sort of my cartoon of stratospheric particles. You have a mode of particles that are almost pure sulfuric acid, and we think from other evidence, not my data, that they're formed by nucleation, new particle formation, mostly near the tropical tropopause, and then sulfuric acid condenses. There's also nucleation onto meteoric metals that occurs mostly in the descending air in the polar stratosphere, the polar winter. And you have organic sulfate particles that are mixing up both through the tropical and mid-latitude tropopause. So those are the three main kinds, and that's 95% of the particles in the stratosphere, and they're very cleanly separated. And we can do this now, we can learn something about the carbonaceous material. Actually, it goes back to the talks by John Abbott and Neil Donahue earlier in the morning. We can learn some things. What I'm going to do is I'm going to look at the size of these two main carbon peaks, carbon and CO plus from oxygenated organics, and that we've blown all the way down. And we're going to sort by the type of particle and look at those peaks, but only in the stratosphere. So here is what we have. So I take the meteoric sulfate particles, and I take the tropospheric particles, and I'm now looking at an altitude profile of the amount of carbon peaks in these things. And there's the really obvious point. The particles formed in the troposphere have more organics than particles formed in the stratosphere. And that fits with everything we know about the amount of organics in the gas phase in the stratosphere. That's fine. But there's a couple of other points we can learn. One of them is here, is that the meteoric sulfate particles that descend into the troposphere start picking up more carbon right at the tropopause. So there's actually some secondary organics going onto these particles even in the upper troposphere. It's not only a boundary layer phenomenon, it's also happening in the upper troposphere. The other thing we can learn is to look at this profile, and these tropospheric particles have as much carbon in them practically when they're 6 kilometers above the troposphere pause as when they first got into the stratosphere. First of all, it means this stuff is not evaporating. In the troposphere, it's a two-way street because you've got all these organics in the gas phase. The stratosphere, you don't. So the organics are not evaporating. They're really non-volatile. The other thing is they're really resistant to oxidation by OH. If, for instance, the rate constant were 0.1, to lose a carbon molecule every time an OH hit a particle, aerosol particle, the particles would last about a week. And 6 kilometers above the tropopause, they've surely been there more than a week, weeks or even months at that point. So whatever glop survives from all this organic chemistry, by the time it gets to the tropopause, it's some really stable, really non-volatile stuff that's left. So the last topic here is the solid or liquid. What is the phase of these particles? And the simple one is the sulfuric acid without metals. They're probably liquid, although there's some hydrates that can form, but it looks like they probably don't. The solid hydrates don't often form in the stratosphere. So that one's the simple one. Then we look, I'm going to go to the mixed organic sulfate particles from the troposphere. And the recent work from Ben Murray and Zobrist Labs and others suggests that the highly oxygenated particles under very dry and cold conditions, meaning like the stratosphere, can form glassy substances. And so it's very probable that there are glassy either inclusions or particles in the stratosphere, sort of based on that laboratory work. And I just put this on. I wonder if it's going to be a new twist on some of the very old electron microscope data from the 1960s. So they collected particles on impactors and then looked at them under an electron microscope. They would look at a particle like this and say that was liquid when it hit it. It must have been sulfuric acid. And they would look at these particles and say they were solid when they hit the impactor. They must have been ammonium sulfate. And that was sort of the 1960s interpretation. And I don't know for a fact, but it may be that these, in fact, may be some of the mixed organic sulfate particles that were glassy when they hit the impactor. I'm not sure. There are also some implications here for the scattering phase function of these solid inclusions. It'll change the way the light propagates through the particles in subtle ways. It doesn't matter a lot for the overall climate impact. The most complicated story is probably the sulfuric acid particles with metals in them. Are they solid, liquid, or both? And here I'm going to go try to turn a disadvantage of the mass spectrometer to an advantage. If a laser hits a mixed particle and it's internally homogeneously mixed, you'll probably get the same mass spectrum regardless of how the laser beam hits the particle. But different laser hits on a particle like this is going to give different ion ratios in the mass spectrum, depending on if the laser hits that inclusion or not. And these are some particles from that Mossop 1964 paper collected in the stratosphere, put on an impactor plate, and then washed to remove the sulfuric acid insoluble species, and this is what was left. And there are these little sort of fractal inclusions in there. They're not soot, they're something else. And in fact, I think perhaps those are the meteoric inclusions that were being seen. But what I'm going to look at, go back to this uniform, non-uniform, and I'm going to look at some of these ion ratios. So this is the ratio of magnesium to iron and nickel to iron, and you could also put potassium to iron in these particles. And this, in contrast, are the silicon peaks and the aluminum peaks with much, much broader distributions. And my interpretation is that the magnesium, iron, and nickel are dissolved in the particle, and that's why you always get the same thing from every particle to particle. And the aluminum and silicon, which have insoluble oxides, aluminum oxide and silicon oxide, quartz is not soluble in sulfuric acid, it's going to form an inclusion, and we're going to see a different amount of it depending on every particle, depending on how the laser beam hit that particle. I'm going to note here that comparing these things, these are as identical as narrow distributions from this instrument as we get with particles we can make in the lab. And in fact, they're narrower than what we see from sea salt. And you would think when there's sea spray evaporating, the sodium to potassium ratio is pretty much the same in every particle. And yet, these particles are even narrower. And one of the things that means, from the ablation point of view, is that these particles, in fact, are more uniform than you would expect from individual mineral grains in different meteors and parts of a meteorite. So in fact, there's mixing between different micrometeors into one stratospheric aerosol particle, and that's because at the low pressures in the mesosphere, gas phase diffusion is extremely fast. And so in fact, you get diffusion between these different meteors into the same particle. So, sort of my summary here, we can determine the source of individual particles in the stratosphere, and it's probably the only one of the few places I can do this with a single particle mass spectrometer. I can look at a stratospheric particle and say this particle formed in the polar vortex, this particle formed near the tropical tropopause, this particle formed in the troposphere, and we can go along and look at those particles. The organic content carries lessons that go beyond the stratosphere. And the reason we can learn things in the stratosphere, we can't learn them in the troposphere, is because we don't have the gas phase organics in the stratosphere. So it's a much simpler system. And what we learn is that the organics in the atmospheric particles are very resistant to loss once they've reached the oxidation state of being in the upper troposphere. It doesn't mean what's happening in the first 3 hours downwind of a city. This is after they've spent a week in the atmosphere. They're really, really stable, and what's left doesn't change for the next months. There's also suggestions about phase. Iron, magnesium, nickel dissolved in the sulfuric acid and aluminum silicon are inclusions. And actually, one thing I forgot to note as I was going through, on these organic sulfate particles, we consistently see there was a little iodine peak off to the side. And actually, I think that's what happens to iodine that gets into the stratosphere, is it goes onto these tropospheric organic sulfate particles and then sediments out of the stratosphere with those particles. And otherwise, iodine, as Susan Solomon showed, is a very powerful ozone catalyst, more powerful than chlorine for destroying ozone, but it doesn't because it attaches in a way I don't understand if it's physical or chemical to the tropospheric particles and then is not available in the stratosphere. So thank you for your attention.
Thanks very much. I'd like to ask a question. I noticed you didn't mention volcanic eruptions, and how do large and small volcanic eruptions affect your results? I assume you're looking at a time when there aren't very many of those. And then what would be the implications for suggestions that we create a cloud there to save us from global warming, so-called geoengineering? Can you make any comments about that?
Well, first of all, on the volcanic, all these measurements were made starting in the late 90s without major volcanic eruptions. What the volcanic eruptions are going to do is they're going to put a very short-lived pulse of ash into the stratosphere, so there'd be another mode that I didn't measure because it wasn't there, and then there'd be a longer lived pulse where you'd see much more sulfuric acid in the particles than you did during the years when I was measuring. In terms of deliberately adding things to the stratosphere, one of the things this is going to tell you is it's going to tell you that part of the stratospheric size distribution is already predetermined, in a sense, by what's coming down through the polar vortices, and you're going to be adding that material. And I know there's modeling by people that say the climate effect of what you add depends on how you add it. For instance, if you add sulfur dioxide, SO2, if you put it in wide plumes, narrow plumes, and it's because of things like coagulation and growth laws are different. And it's going to put a little bit of a twist on. It's not going to change it a huge deal because most of those things are near the tropopause, talked about near the tropopause, where there are the fewest of these particles, but it will, both the meteoric material and the fact that there are tropospheric particles coming up means that if you're going to model that addition, you shouldn't just be modeling sulfuric acid nucleating in the stratosphere, because that's not the whole story.
Yes.
Can you say anything for your measurements about the oxidation state of the carbon in the organic aerosol that's entering the stratosphere and the troposphere?
Okay, the question is whether I can say anything from the measurements about the oxidation state of the carbon that's entering, and I have sort of crude measures like the relative size of the CO plus peak compared to the carbon peak, and also in the negative ions there's a little more information. The answer is it's highly oxidized, and I can't say very much more than that.
Natasha?
Will you see the difference between wet stratosphere and dry stratosphere and behavior of the particles?
The difference between which two?
Wet and dry. Does water vapor make a difference?
Pretty much all. The way I'm stratifying these above 17 kilometers, it's all in air that's very, very dry. And so for the most part, I'm not seeing any influence from water in these data.
Speaking of coagulation and condensation, sulfuric acid part condensed on a nucleus of the metal, or whether you're just seeing the metallic particles coagulate with a nucleic sulfuric acid mode that grew up to the size of the particles you see.
The question is, can I see when we got these, when we got multiple nanoparticles in the sulfuric acid, before the sulfuric acid condensed or after? And I'm not sure from looking at the chemistry of the particles you can tell. The modeling suggests that there should be coagulation in the mesosphere. And if you can believe some of the electron microscopy, if you can believe that one electron microscope image from Mossop, it would indicate that it happened before you went in. But there aren't really any good data. It's really, the modeling would suggest, the coagulation rates would suggest it should happen before they start descending in the winter polar vortex.
Okay, thank you very much. As our last speaker, David Nealon, comes up, I just wanted to remind you there's going to be a ceremony tonight where all the new fellows are honored, and also that the deadline is March 15th for submitting nominations for new fellows for next year. Our last speaker is David Nealon from UCLA.
Thanks. I'm going to be touching on a rather large topic, the sensitivity of precipitation in climate models, and I'm going to be doing it just by sampling through three topics that I'll try to link. One is basic indication of how sensitive things can be, and some of the ways that you can attempt to do statistics in a way that favors the models or not. The other is, as you perturb parameters in the model, there's a substantial community looking at uncertainty quantification, and I'll touch on some things you can say about multi-model ensemble mean and what you would expect to infer from the techniques we use to address the models. And third, one cut at reducing model uncertainty by doing observations for the onset of strong convection. Now, there's a big community that's been working on this for a long time, so let me just touch on a few of the, let's see, the laser pointer is not pointing, touch on a few of the things that have been done before down at the bottom. What we're going to be pulling out here is the model disagreement in a way that I've been showing for a few years, and then looking at the way that amplitude or large scale shows better agreement or agreement on sign, using, for instance, El Nino teleconnections as an example. Here we have an example of a climate model change under global warming, with the red colors showing decreases in precipitation for the end of this century under a certain scenario, RCP 8.5, for the increase in greenhouse gases and other forcings, and the green and blue showing large increases. These are substantial, on the order of 3 millimeters per day. For instance, at the edge of the convection zone is basically a shutdown of the edge of the convection zone. As we go through a series of models from the current CMIP 5 Coupled Model Intercomparison Project 5 archive, you'll see that there's considerable jumping around in this simulation of June, July, August precipitation. So these are the different patterns. If the models agreed, you would only see the model acronym changing. The thing that we're looking at here is an ensemble average over these models, a common way of assessing these. The amplitude is considerably smaller. On the other hand, you get the average of the models agreeing. What can you say about this by looking at other aspects of the climate system? Here's a more typical way of assessing the agreement among the models. This is referred to as a Taylor plot, and the angular axis here is the spatial correlation, in this case, of each model's end-of-century precipitation change pattern to all of the other models averaged to produce the dot for that model. The fact that you're getting correlations as low as 0.1 and not much higher than 0.5 for the models is an indication of that disagreement that we just saw. The red dot here is the multi-model ensemble average, and the thing to notice there is that the amplitude of that is considerably less than the amplitude of each of the models. So we might want to use a multi-model ensemble mean for assessing the best guess of the spatial pattern. You want to be careful about the amplitude. Of course, the multi-model ensemble mean has to be less than the individuals, but we can say something about that from a couple of different aspects. Now, one of the main ways that this change under global warming is discussed is sometimes referred to as the rich get richer mechanism, a name that we're responsible for launching, but which has had a number of much work on it since then. Essentially says the regions that are already getting a lot of precipitation due to moisture convergence will get more. The regions that are already getting little precipitation due to moisture divergence in the climate will tend to get less. And this scatter plot here is a way of visualizing that with the end of century change on the vertical axis and the precipitation minus the evaporation from a base period climatology on this axis. If you look at the moisture change at the end of the century times the mean convergence, the moisture change is going up just due to Clausius-Clapeyron considerations, and you get a pretty good relationship to things you can evaluate from the base state. In other words, you simply add more moisture and converge it with patterns that you're used to, and you tend to produce an increase of precipitation in the regions that already get a lot, and vice versa. When you look at the total change in precipitation, or precipitation minus evaporation, it has much more scatter, and this scatter refers to the differences that you're seeing regionally. What's happened there? Essentially, you've had changes in the circulation, especially in the convergent component, simply because you don't only have the moisture budget to consider in these things. You have criteria for the onset of convection. You have the energy budget to balance as well, with various forcings in it that are spatially inhomogeneous. And in the end, you end up with something that has a tendency to follow locally this simplest rich get richer rule of thumb, but many departures locally that need to be addressed within the community. I should mention that this is shown for seasonal changes relevant to the monsoon, and I'll be talking about this in the monsoon session. So caveats on the simplest statement. But what if you take something from observations, El Nino Southern Oscillation, and you decide to take the teleconnection patterns as a prototype for how the models do at precipitation change processes when faced with a warming signal, such as happens during El Nino. And there's a poster with details on this by my student Baird Longenbrunner on Friday. If you do this Taylor plot format, you see slightly better agreement than on the global change problem, and this is agreement with the observations, but not all that good. You're looking at top models around 0.7, and not that much change from the set of models used 5 years ago to the set of models that are being assessed currently for the IPCC Fifth Assessment Report. These are assessed for different regions that have strong teleconnection signals to look at. So similar problem with the model getting the exact spatial pattern, but once again, the model amplitude is better than the multi-model ensemble mean amplitude. Here's a blow-up of that, taking into consideration these many dots, things assessing the the natural internal variability impact. But by and large, bottom line is, models do pretty well at amplitudes, even if they don't do that well at the specific exact spatial pattern distribution of the rainfall anomaly. And that would be good news if you're trying to infer the likely amplitudes of the global warming change, if you can use that analogy to ENSO. How about agreement on sign, another commonly used index here? The top is the agreement of the models with the observations for the El Nino teleconnection signal, and you can see that they get high agreement over broad spatial regions. In fact, broader spatial regions than would pass t-test. Binomial test works pretty well here in predicting where the models will give a good prediction of the sign. So that's also good news in terms of assessment of future precipitation anomaly, if you can use that analogy. Okay, second topic, take a slight step to one side and look at the perturbations in just two climate models, to the parameters within that climate model, and the range of possible precipitation simulations or change patterns that are spanned by this. You're interested here in things like how nonlinear is the precipitation sensitivity. If it's rough, that's bad news because you would expect even the smallest change in parameter to potentially impact your solution. If it's smooth, there's a number of techniques you can borrow, for instance, from the engineering literature to look at this. For a special case of rough parameter dependence, there's a poster tomorrow by Chakroon et al. All right. Just to mention that there's a lot of activity going on in this field, a set of other players in this area. But one of the big things is if you need to assess your climate model sensitivity to a lot of parameters, if you sample by brute force through a parameter space with, say, 10 points in each direction, you have n parameters, you get 10 to the n problem increasing with the number of parameters. But if you have smoothness that can be fit by a quadratic metamodel, entry level from the engineering literature, then it brings it down to an n squared dependence, something that you might actually get a handle on. And you can also borrow techniques, I won't be going into the details of this, with a multi-model objective, which just means assessing each field and region as its own quantity and looking at the trade-offs between improving them or looking at the sensitivity in them. Here's two samples from a particular climate model, the ICTP AGCM. Run for 250 years as an ensemble, in this case with observed sea surface temperature, as a function of just two sample parameters, one affecting cloud albedo, one affecting convective relative humidity, and when the convection fires in terms of the lower free tropospheric relative humidity. This is what you would like to see, a nice smooth dependence. By the way, the vertical size of these dots is the standard error in assessing this. A nice interior minimum. When you look at this convective parameter, you find that the nonlinearity is so strong that it actually reverses the curvature of the objective function. I'll show you fits here, one with a linear meta model for the spatial and seasonal fields with a nice minimum here. And the other fit here with the linear has the wrong sign, and you need to go to a second order quadratic fit in the spatial fields in order to get it. And the bottom line of this for our purposes here is you do not want to do blind optimization in these systems, but the techniques borrowed here can be useful for telling you where to look at your parameterized physics, in particular at the very high relative humidity interaction of convection plumes with the relative humidity before it fires will be a very sensitive region. And second, that you're strongly nonlinear, which can feed back on our statements about the multi-model ensemble mean. So, in a single model, if you're perturbing the parameters, you have a prototype for an ensemble of models such as we were seeing before. In fact, you can force this to be true if you create parameters that lead you from one model to another, not done in practice, but in principle. If that parameter dependence is A, linear, and B, the average of the parameters assigned by each of the models is unbiased with respect to the best fit to observations, a multi-ensemble mean should be perfect. But if we represent this as a diagram with one parameter here, another parameter here, viewing our different climate models as different points in this parameter space, if you have nonlinear dependence on parameter, a multi-model ensemble mean will always be biased. Second, if you have the situation where in one of your parameters the best fit to the observations, as we saw was the case with the convective parameter, tends to be at one end of the range that you guessed a priori, you're going to have a strong bias within that ensemble. So what you need is ways of assessing the nonlinearity, and second of all, 1,000 different constraints that will reduce the space, the possible space of your physical parameterizations in your model. Let's show this a different way. One is to use our meta-modeling approach to split up the difference in the global change signal into linear and quadratic contributions. In this case, this is an atmospheric model coupled to a mixed layer ocean run in the standard way for doubled CO2 minus pre-industrial contributions. Take the difference of that, and then evaluate the change between running the model with one value of the convective relative humidity parameter versus the standard value. The size of this is large as the differences we saw between those models at the start, indicating that it's a reasonable prototype for that type of behavior. The fact that we have a strong nonlinear contribution has implications for not using multi-model ensemble means to assess everything, at least, about your expected change under global warming. The fact that this is a complex spatial pattern also means that you're going to have a challenging job as you try to, say, optimize your models for best fit to observations in the current climate. Here's just an example from another model. This is the community atmosphere model, in this case run with observed SST, just evaluating the sensitivity to entrainment. And again, highly nonlinear sensitivity here in the comparison to observations for column water vapor, and this is the spatial pattern of that sensitivity. In this case, fortunately, it saturates at high entrainment, and so, as we'll be showing next, if we can eliminate the possibility of low entrainment being consistent with observations, you'll have a considerable reduction in the possible space of what you would predict for future climate. All right, so let's switch to that. Using a different set of observational constraints, so this is our third and last topic, you can take the observations, for instance, at the narrow arm site for precipitation and column water vapor. Why column water vapor? Because we have lots of satellite microwave data for it. If you bin the precipitation and do the conditional averages for each bin of column water vapor for a given temperature condition on a large scale, you will have an onset, a rather sudden onset, as you get conditional instability for high enough water vapor. This has everything to do with the fact that as you go into the lower free troposphere, you're entraining the environment. If it's dry, you kill your convection. If it's moist, your convection can take off. You have some suggestion that entrainment is an important parameter already here, because if you use an entraining cape, you can match this onset in your column assessment of the instability. If you use a non-entraining cape, you would suggest that this would all be unstable and you should be seeing heavy deep convection everywhere. Let's take this into a modeling framework and see how consistent this is with one particular model. First, let's use microwave observations so we can get temperature into the picture as well, because you need a lot more observations than are available at one arm station. This is doing the same conditional average as a function of column water vapor for precipitation on this axis, but for different temperatures using a bulk tropospheric temperature to separate between them. There's a sudden onset, as you expect, as you hit column convective instability. You can characterize that by fits that are borrowed from techniques from the statistical physics literature for looking at large ensembles of interacting things, in this case, columns of precipitating columns. If you collapse that water vapor axis just by normalizing by the critical value for the onset, you get a nice collapse of various observational quantities, the onset for different temperatures, the high variance near that onset, and the probability of precipitating points as a function of that collapsed water vapor. So we can use this important critical onset value as an empirical test for the models. Let's set it up in a different format. This is the tropospheric temperature on this axis, the column water vapor at which you have that critical onset on this axis. In other words, you're just taking from this diagram all these onset points and putting them on this diagram. It has a different dependence than, say, column saturation, as you expect, because it's the empirical quantification of where you got convective onset for the typical type of entrainment you've got in your observed column. Here's the model. It has a linear pickup rather than the curving one here. That's not of concern today. The point is that for the standard values in the revised version of the community atmospheric model, you have this onset approximating pretty well the temperatures and water vapors at which you have the observed onset. Here's another view of it here, put on this temperature water vapor plane with the model onsetting at about the right place. And then you can grab the model entrainment scheme and check that you can reproduce this for current values of entrainment. Then you can turn down the entrainment, and as you move to lower entrainment, you find that you would get a ridiculous answer for this, completely inconsistent with observations. In other words, the entrainment that the model currently has is doing a fairly good job at this convective onset. That eliminates that highly nonlinear regime as you move from low entrainment to higher entrainment that we saw as a function of the model parameter sensitivity. So if I can just recap, the particular string here was to say that we still have very substantial uncertainty in regional precipitation, particular for global change predictions, although you do better if you back off and try to just look at amplitude or sign or large-scale regional averages. In our parameter dependence, we don't have the nastiest case in some of these important quantities. We have smooth enough that you have tools to look at it. However, there is substantial nonlinearity in certain parameters, suggesting that you want to be careful about just using multi-model ensemble means to evaluate things for global warming case. And finally, we illustrated one of what will have to be 1,000 cuts in reducing the plausible range of parameters in the physical model parameterizations to use new statistics to eliminate parts of the range that you would currently consider running your model at. And that should eventually take our uncertainty down considerably if this is a good prototype.
Thank you very much. Do you have any questions? Yes.
So the question was essentially, what would you do instead of a multi-model ensemble average just with the data in hand? There have been various attempts by a number of investigators, some of whom are in the room, to try to look at, say, simulation of climatology and eliminate models with a really bad climatology, for example. That has met with mixed success overall. It's a good idea to be evaluating the models, but in things like teleconnections, it doesn't necessarily work. The thing that I would be suggesting here will take a little longer, and that is to be using the perturbed physics ensembles for many of the models to evaluate where the nonlinear differences are among the models, and then really focus on constraining that physics, the ones that are most tripping up what you would do in a multi-model ensemble mean. And that'll take a little longer, but it's something that's entirely feasible for the community to do.
Okay, thank you very much, and I'd like to thank all the speakers, and let's be sure to congratulate them at the award ceremony tonight.